Hey, thanks everyone for coming over. I appreciate your time. Today's topic is called How Hard Is It to Solve? The word hard here means something special. So that's what we are going to dive into. But before going into two quick plugs, if you look at my bio, you might have noticed that I have one book up in Amazon and other places that you can buy called Thought Experiments. Working on my second book called Oil and Water. It's about energy policy. I used to work in an offshore oil platform in my previous life. So how is life in an offshore oil platform? And then dovetailing that into world's energy policy and how things shape up, right? The book is going to come out maybe in the January timeframe. I'm done writing it, but it's going through publication processes. But just to promote the book, set up this website called Oil Water Book, easy to remember, .blogspot.com. Like people are saying, I'm trying to use a lot of AI tools in creating this book. So if you just go to this site, you would see a bunch of simple audio intro about what this book is about, right? So it's in English, Chinese, Tamil, Spanish, any kind of language that you can think of. Use AI tools to create it. And then there is even a link there using which you can interact with the English version, ask questions, and then it will answer you. And rather than, it's not like a simple podcast that you need to listen to, right? You can ask questions and it answer a lot of things. So try it out. When the book comes out, I'm not making a penny out of it. All the money goes to charity. So buy it, gift it, help me out. I mentioned this in all my talks because this is really good for students and faculty. There is a website called Network Builders that Intel maintains. It has about 400 courses. When we say courses, it's basically something like this lecture given by subject matter experts in whatever area that you want to learn things about, AI, ML, cybersecurity, mobile communication, etc. Then it will be followed by a quiz, right? Quiz is pretty simple. So you can take it and then try to gather more and more knowledge, particularly students going towards interview phase of your life. You can check it out to see if that could be of use. And then out of those 400 courses, there are also some that are strung together. For example, let's say you are interested in cybersecurity. Out of 400 courses, there may be 20 courses related to this. They are strung together to form what's called a pathway, custom pathway. So you can choose that and then complete it to get the complete knowledge about one particular domain, right? And the cool thing is it's all free. You don't need to pay any money, anything like that. And it's not meant to promote Intel technology and products alone, but are meant to educate anyone interested in these topics, right? So check it out. Similarly, I keep listening to this one podcast called Packet Pushers. You may be familiar with that. If not, check it out. I don't get paid by it or anything. I just think it's a collection of good podcasts. There are things about IT management, networking, anything, leadership. How do you manage IT teams and so forth? Different podcasts that are there. So whatever interests you, you can check them out when you get time. Okay, coming to the topic, what is it that we are going to talk about, right? So this is about problems. So I originally put this talk together because within Intel, when young engineers come in, if I ask them about problem complexity, they usually drew a blank, right? They didn't know much about it. So I think it's really important for people in any IT world, software development, even hardware, to have a general idea of this class of problems and how hierarchically they form a series, so that when you come across a new problem, whatever it may be, maybe a database analysis, you want to sort some records, you want to do protein folding in biology, whatever the case may be, you need to be able to understand how easy or difficult it is to code. And when you code it, can you really get to the perfect answer for that solution for that particular problem, right? So there are a lot of things to discuss about the problem types. That's what this talk is about. So we'll introduce this notion of Turing machine. Then we'll talk about this P and NP class of problems. And that dovetails into quantum computing, because we developed all these hierarchy thinking about the standard form of computing. So now quantum computing is coming in. So how is it going to mess this all up, or all these hierarchies out the window, right? We'll talk about that. And then how do you prove something is NP complete, which is critically important? Then we can do Q&A. If you have questions, feel free to stop me. I'll try to answer them. So I've tried to build this from a very simple problem onto more and more complicated problems that are out there. So let's just start with just like adding and multiplying two numbers, right? So this is just some random two decimal numbers. First one is adding them, second one is multiplying them. So you know this is elementary school mathematics, right? So you know how to do it. The point is how much of time plus space effort that is needed to do this computation. If I ask you this question, in case of the addition, you literally know you are going to add these two numbers, put this here, take the carry, blah, 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 and then loop through this till the end, and then you got the answer, right? So this is very deterministic, very simple problem, but extremely clear. We know how to do it. You can code it up, and you know how long it's going to take in whatever unit of time you are going to measure. If this is taking 1 unit of time, then this is 2, 3, 4, 5 units of time. You can finish this, right? You know that. So you can define the time it takes to do this particular problem by the length of the number of digits in that number itself, whichever number is longer, right? So it's as simple as that. If you're going to do a multiplication, then of course, you know, you need to multiply each one this way, add it all up, etc. So here it's a little bit more, but still how much time effort you are going to take is defined by not the value of the number, but how many digits are there, right? So a 2-digit multiplication is going to take a lot less time than a 10-digit multiplication and so forth. But it's very clearly defined. So if you take the number of digits in the number as n, you can define the time it's going to take in some version of n, right? So maybe 1n, 2n, 10n, whatever n that you need to come up with. And how much space it's going to take. By space, we literally mean like, okay, you need, maybe if you're programming it, maybe this is stored in one location, this is in another location, then you need a third location to store. Whereas here, maybe you need like 5 registers additionally to do this multiplication, right? So that's time and space. Those are two things that we are trying to look at, how much time and effort you need. So this is extremely simple, right? So we start. Then keep going into something a bit more complicated. So let's take sorting numbers. So you have a bunch of numbers that you need to sort. I'm sure you all know bubble sort. So you have 10 numbers randomly mixed up. If you want to do bubble sort, you start with the whatever one end of the array, and then just keep looking at whatever is the smallest, right? And then you keep switching, find the smallest one, put it on top, then go down, and again look for the next smallest, and then put it the next one, and keep doing that, right? That's bubble sort. So basically you're bubbling up the numbers one by one, and then by the time if there are 10 numbers, you do this 10 times, then you are done. And then since there are 10 numbers, you're also going to do 1, 2, 3, 4, 5, go up to the top, that's 1, and then second number and third. So roughly it's n square, right? So there are n numbers, so it becomes n square. That's the time that you need to complete this computation. That's bubble sort. So is that the best you can do? Absolutely not. This is an old problem. So there are merge sort, quick sort, all kinds of sorts, and we come up with n log n, meaning instead of n square, it's n and then log n. So you are shrinking the amount of time that is needed to do the computation, right? This is really, really important. Often in classes, students may be taught, oh, this is bubble sort, this is merge sort, quick sort. They learn, they code it, and then move on, right? But the order notation, meaning in terms of the problem size, if the problem is of size n, meaning if there are n things that need to be sorted, how much time you are going to take, is it n square or n log n, makes a big difference as the number of the problem size increases, right? So if you have 1 million social security numbers that you need to sort, right? As some database record. It's going to take a lot of time if you code it using bubble sort. Maybe easier, but that's not a good way to do, right? If you do the better sorting methods, you will do it, get it done much, much faster. So you need to develop this innate notion of how much time, space do I need to do any kind of computation that you are involved in, right? So let's continue further. What more problems can there be? And if there is all these different problems that keep coming up, how, I mean, can we develop some sort of a standard way to measure or assess to get an idea of how complex a given problem is, right? To do this, Alan Turing in 1936, almost 100 years back, came up with this theoretical computer model called Turing machine, right? You might have also heard Turing test in the context of AI, where the machine can mimic a human being and so forth. Earlier in my grad school, it took me 2-3 days to realize, no, this is different from Turing test. Both are attributed to Alan Turing, brilliant mind, right? So the idea here is there is a long tape, right? And the tape is segmented into cells. And the cells have something written, and then you have a head. Think of it like a cassette head kind of thing, right? So it can read what's written in a particular cell. Then you basically give a program to the to this finite control. So it's basically just a table, right? So you are starting at some point, then you are reading what's in there. And depending upon what's in there, maybe you will rewrite that, or maybe you will move to the right one step or left to the left one step, or you will move further, whatever. So there will be some instruction given to you depending upon what's written there. So you move, you do that one move, right? So maybe you start here, it says x1, I mean x2, that means move to x1, and then here maybe it needs to move to b. So for example, if this is an addition problem, it might mean take the first digit of this x2, add it to the first digit of x1, and then write it here, something like that, right? The basic idea is using this simple model, you can code. I mean, this is what is happening in a computer. It's a very abstract, thinned down, simplified model. So this immediately tells you how long it's going to take and how much space you need to do any kind of computation, right? And this is just a more elaborate version of it. So you can see sort of a table that is here. So this is the tape. It's actually moving, and then something gets read. It comes here, looks at it, figures out what needs to be written, and then move left or right and keep doing that, right, repeatedly. This is enough to pretty much do any kind of current problem, be it a model, you are doing a neural network, whatever it may be. It can still give you an idea of the time and space needed to complete the computation, right? So this is called universal Turing machine. And people have tried to actually develop some manifestation of it in reality also. But whenever you create a real version, it's all toy, because the universal Turing machine is supposed to be infinity on either end. So you can keep doing this computation forever, right? And that's Alan Turing. He showed that once you have this, you might immediately think, okay, now give me any problem. I'll tell you how long it's going to take or how much space is needed to do that computation. But it's pretty much decided, or like it's been proven that simply if you give a program, even figuring out whether this Turing machine will eventually come to a stop or not is not possible to decide. Okay, this is called like decidability problem. It's like whether the Turing machine will halt or not itself is not decidable. What do we mean by that? This helps you try to keep classifying different kinds of problems in different hierarchy, right? That's what we are basically moving towards. So some simple problem, if you are saying addition, multiplication, yeah, you know how to do it. And even if you give like 100,000, 1 million digit numbers, you know how to do it, and you know when the Turing machine will stop. But you keep making the problem more and more complex, pretty soon you get into areas where it's impossible to, you can code it, but it's impossible to say whether this program will ever come to a stop and give you a clear answer, right? So I'm going to use this simple puzzle over and over in different parts of the lecture. So just take a look at that extremely high school mathematics kind of puzzle. So there is a 5-digit number, right? It's A, B, C, D, E. Each A, B, C represents one digit. If you multiply that by 4, it gives you an exactly reversed version of that number. It becomes E, D, C, B, A. With the paper and pencil, you can figure out what this number is in 5 minutes, right? So not a big deal. But think how you can solve this problem. So if in a very simple way, since this is a 5-digit number, you can basically start with 10,000, right? 10000. Multiply that by 4, you get 40,000. No, that's not a reversed version of 10,000, right? So that's wrong. So give that up. And 10,001 multiply, no, it's 40,004. No, that doesn't work. You can keep going until 99,999, right? And somewhere in between, you are going to find that right number when you multiply by 4. It gives you the exactly flipped number. Why are we talking about this? So you can code this as a while loop, take 10,000, multiply, then doesn't work, add 1, keep doing it, right? That's like bubble sort. It's like a brute force method. It will work in this case because it's like a 5-digit number, so it's not going to take too long. You can figure it out using a good computer. But even if the same thing, if I am saying it's like 10-digit, I don't even know if there is a number there or not. It's going to take far, far longer, right? So what can you do efficiently to reduce the search space so that you are doing it more and more intelligently, right? Some simple thing you can look at it. Look at this is it's A, B, C, D, E. That's 5 digits. When you flip, it still is 5 digits, right? So that means if A is anything bigger than 2, right? If it's 3, when you multiply by 4, it's going to become 12, and so it will become a 6-digit number. So A cannot be anything more than 2, right? So it has to be 1, 2, something like that. So that gives you one way to like cut down the search space. You initially had 5 digits and then 10,000 to 99,999. Now you deleted so many of that, and the search tree for you became much smaller, right? And then, of course, when you flip it, the multiplying E gives you A, right? Because that's on the right side end. So again, you can start thinking, what are the numbers that when you multiply by 4 is going to give you an acceptable number? So another way to shrink it down, right? So from 100,000 number that you are quickly shrinking the space down. If you actually sit down and do it, you'll do it in 5 minutes, right? So it's not a big deal. So when you write a code, you need to write the code that way. You need to figure out how to do this more intelligently, and then you cut down the space, and then you get to the number much faster. That is equivalent to doing your algorithm correctly. You are moving from bubble sort to quick sort and so forth, right? Keep this in your mind. Here, one thing that we can notice is computing this and coming up with that answer is fairly difficult, right? But if somebody says, hey, this is the answer, verifying that the answer is correct is too trivial, right? You just take the number, and Brian is telling me it's XY, whatever that 5-digit number is. I just multiply that by 4. And if the number is flipped, then yeah, okay, you're right. It's good, right? So there are problems where the actual computation is really, really difficult, but verification is really, really simple, right? And you might think this is the case everywhere, but it's not, because often you'll come up with some problem, it gives you some solution. You don't know if that's the really correct solution or not. Maybe even figuring out whether it is the correct solution will take you a lot of time and space, right? So you need to put these problems in one class where computation is difficult, but verification is easy, right? I hope I'm making sense. If something doesn't make sense, stop me. So now let's move to a totally different kind of problem. tiling a surface. So I'm giving you a small rectangle, right, like a brick, or even take this hardwood floor. You have a long rectangle space. So I'm asking, hey, can you use this space and cover this entire room? Trivial. Yeah, okay, just put one next to the other and keep expanding until you finish the room, right? Okay, that's like addition problem. But what if the shape is like this, right? You think for a second, then you realize, if I actually flip it around, put two L's the other way, you more or less get a square, and then you repeat that square, and again, you can cover whatever space that you want, right? So you're good. So, okay. What if I give you something like this, and these are all pieces, okay? There is a hexagon, there is a square, there is a triangle. Then you can slowly assemble and then create maybe some shape, and then you repeat that shape. If you can make a perfect square, fantastic. Then you can repeat it, and then it becomes really simple. But what if it doesn't become a perfect square, right? So if it becomes some odd shape, can you still continue building it? And then it's not one room. I'm saying write a code that will, expand this to infinity, right? Repeatedly, this is something we all will quickly miss. If you give you a number to add, just adding that's trivial. But even if I say it's 1,000 digits long, adding that is okay. But the question that we are always trying to answer is, irrespective of the problem size, irrespective of how big that number n is, it can be 1, it could be 10 million, billion, whatever. Can we still come up with some assessment of how difficult the problem is? Whether we can actually write code that will solve the solutions, find the perfect problem, perfect solution for this problem or not. So if I give you all this, can you do it? And then what if I keep adding conditions saying, hey, the adjacent colors cannot be the same, right? Or maybe in particular case, the adjacent color should be same, some such restriction condition. Can you still do this tiling consistently? Can you develop a code that will fill that entire infinite space surface by tiling? So in all these cases, immediately the combinations explode, right? Meaning there are like way too many options. That's why I was starting with that 10,000 to 99,000, like we have 100,000 whatever options. So when the numbers become bigger, it suddenly becomes too big for us to fathom, for us to understand. But can we still write code? Can we still figure out the perfect solution in each one of these cases? Brute forces may not work in most cases, right? That's why I started with that ABCDE problem. Brute forces 10,000, 10,001, 10,002, all the way to 99,999. It may not really work in a reasonable amount of time. This is something that we are depending on when we do cryptography, right? So I'm sure you all heard that the security is dependent on the complexity of the key that's given to you, that is used in information exchange, maybe a banking transaction, all that uses that cryptography. And if that computation, what the answer, what the key is, if it can be broken, if it can be figured out what it is, then the whole security system just collapses, right? So we are depending on the fact that for any computer, a supercomputer, whatever latest technology that you may have, it's still by brute force, it will take you 1,000 years to break one key, right? That is the strength we are dependent on for this whole security system to work right now. But what if we can come up with some newer version systems that actually resolves those issues much more, much faster, right? Then some of these security things becomes, full of holes. It's not so reliable anymore. That's where, again, understanding the problem complexity and how difficult or how easy it is becomes really important. So when you really go into the actual solution, how did you code it? If you start your computer to start working on a given problem, is it going to run through and then eventually stop? That itself is, that's called like the decidability problem and the halting problem, meaning the Turing machine, will it ever keep running and then stop at some point? it's undecidable for a random program, right? So if I give you a simple code that adds two numbers, you can write a code that will examine that particular piece of code and tell you, yes, this will come to a conclusion. It will come to a halt. It will tell you the answer and stop, right? But you cannot write a program that will analyze any program you give for it to analyze and then tell you whether it will come to a conclusion or not. That is the halting problem that we were talking about. So we talked about addition, multiplication, sorting, then we are talking about tiling. Jump to the next step. This traveling salesman problem has been, it's easy to understand. It's been around for a long time. A simple idea. There is a traveling salesman who starts from maybe the headquarters or wherever he's living, had to travel a bunch of cities, right? And then come back home. To do that, what's the most optimal way, right? That's what you're trying to figure out. Maybe you want to reduce the distance, right? How much that he has to travel to the minimum possible. So if you just have two cities, you're in A and B, problem is trivial. You just go to B and then come back. There's nothing to really figure out. If there are three cities, you can go ABC or ACB, and that's about it, right? So those things are easy. But as soon as you go to 4, 5, 6, the number of ways in which you can travel and come back starts to really expand. It becomes explosive in combination, right? So this puts traveling salesman problem in another class where if the computer is written, given a code that by brute force, meaning go from 1 to 2 to 3 to 4 to 5, all the cities come back, and then maybe go to 1 to 3 to 5 and then come back. You are going to do it by brute force and then assess how much time or the distance it takes. Again, it will work for maybe smaller numbers, but as the numbers increase, the time it takes just shoots up, right? So it becomes way too much and you can't really do that. It's not going to work. So there are problems which are kind of trackable, meaning you at least understand and you can figure out where is it going? Can I write some code, get to some level, something, right? So that's kind of a trackable level of problem. And then there are actually intractable problems. So anything that you do simply, addition, multiplication, or tiling, etc., those are all tractable problems. At least you know what's going on. You can figure some things out. But there are problems beyond that are intractable. You don't know what the hell that's going on. It's way too complicated and way too difficult, right? And then there are decision problems, which is like the halting problem. Given this code, is the Turing machine going to stop? Or we can even restate the traveling salesman problem. Let's say he has to touch 25 cities. Can he do it under 1,000 miles, right? So then it becomes a decision problem. It's just an yes or no. Can you find out a way in which it's less than 1,000? Maybe it's not the most optimal. Most optimal is 700, but you came up with something that's less than 1,000, good enough, right? So if you can do that decision problem, the answer should be yes or no. So it's like that. Or you want like full optimization. So if you take traveling salesman, you want to make sure it's the least amount of distance that's traversed, right? Or maybe the least amount of time. Why is this important? Is it really needed? Can't you just go in some way? No, because if you just take UPS truck, every day, I think the drivers make, I forgot how many, like 70 stops or something like that, or 130. It's like really close to like 100 stops in one day, right? They optimize things like they always go right. So even if there is a house here, like doing all right turns and then coming to this, even though if it's closer, is more optimal, saves petrol, saves gasoline, saves time. It's much more efficient. So is that, I mean, it really translates to dollars and cents, right? It actually translates to money in the bank, the time it takes for the computer to figure things out. So optimization problems are really important. But we said in case of even traveling salesman, between like 5, 6, 7, the combination shoots up. So if you have 100, figuring out every which way the driver can go And again, you may not be optimizing just for distance alone, right? Maybe for time also, maybe for gasoline, because you don't want the driver stopping at every red light before he finishes the route, right? So figuring that out takes too much time. So what do? Then you need to come up with some heuristics methods to figure out how to do this, right? So that's what this whole thing just tells us. So there is this article called on Quanta magazine. I just created a shorter URL that might be easy to remember. It's like slow computing. So I just called it slow com bit.ly. So you can just go there and look that up. It talks about different Turing machine code that are repeatedly being written to see how long it may take for the Turing machine to stop in any particular problem. It's a very interesting article, not a difficult read, just a couple of pages long. I'd encourage you to look at it because it talks about Turing machine, decidability, how long it takes, optimization, all that stuff. So going back to that ABCDE problem, remember we said that problem, since it's only 5 digits, it's easier to do, right? You can clearly do it. So any of those where that size of the problem n being the number of digits or whatever the number of cities that you need to visit, whatever it may be, that n, if it is the number, it's not in the power value, then I mean the amount of time it takes to solve that problem, if it's in n square, n cube, n power something, n power some constant, then that is, all those problems are called polynomial time solvable problem, right? So they belong to this class P. Those are sort of the easy ones. The next bigger version is NP, which is non-deterministic polynomial time. So here, these are the verification is easy, but computing is difficult class of problems, right? So imagine ABCDE. If I tell you this is the answer, just verifying whether that answer is right or not, that doesn't take too long, right? So somehow, if you can find a way to explore all those 10,000 to 99,999 paths in parallel, and then just pick the one up that's the correct one, then the time it takes is only 5 units of time, because there are like just 5 digits in that number, right? So that's the time it will take for you to verify if somebody tells you. But imagine if there is actually 100,000 processors that are working in parallel, figuring out each one, and then one says, hey, I got it, right? So if you can make things do that, fantastic. Then you can actually solve it in polynomial time. But you need this non-deterministic computer, meaning depending upon, I mean, in this case, it's 99,000, but traveling salesman, it might become million, trillion, whatever. So you need so many processors working in parallel to get to that. So that's it's not practical, right? So it's not going to work. But if you have some such model, then you can solve it in polynomial time. That's why instead of saying, come up with a computer that will have so many processors working in parallel, we just say verification. If you can just verify in polynomial time, then it's non-deterministic polynomial time problems, right? And the P, which is just polynomial, it's a small subset of that NP class of problems. Okay, hope I'm making sense. So then there is this NP hard. So these are another class of problems that are even harder, but there is some intersection between these two. And this is called NP complete. So in today's lecture, if there is one word that you should remember, you should take it with you, it's NP completeness, right? So why is this important? Because if you can solve any one problem in this space, there are a lot of problems here. If you can solve one, you can use the same solution to solve every other problem in the NP-complete space in polynomial time, right? So basically, it gives you a way to solve all the problems in that domain if you can figure out how to solve any one, because the others can be reduced to that particular problem. So as we said, this polynomial is the easy one, right? And then that NP is medium, and then NP complete is difficult, and then NP hard becomes really, really difficult problem. So you're starting to build a hierarchy of problems out there, right? And this is given a problem, can you find a solution? If it always works in n square cube, whatever it is, even n power 1000 million, we are okay, because it's not going to rise that quickly. It's not exponential, right? So if it is the case, then you can find a solution in P. We are happy. That's within our control. We can develop solution. You can develop computers that can actually do that. If it's not possible, then you get into this NP area. But for example, there is this game called Go that you might have heard, like chess. It's another game called Go. It's already beyond this, right? So if you really want to solve that, you cannot write a perfectly clear algorithm, program it, and then it will always find you the perfect optimal solution. Not possible, because there are way too many combinations, right? So people have thought about it, and then we have come up with this hierarchy of problems, right? So here this BPP stands for bounded error probabilistic, and then polynomial time solvable. This regular is the easiest one. This is context-free languages. Then we have P, NP, P space, blah, blah, blah. It keeps going up. So in the end, you have these recognizable, meaning we understand what the problem is, and that's about it, right? It's like totally hopeless. So here, the interesting thing is this P is polynomial time, and then this NP is non-deterministic polynomial time. And we are saying if you can solve one of this problem in a reasonable time, then you can solve all the problem in reasonable time. And if you can do that, of course, P is inside NP, so it's all the same. So people have been struggling to figure out if this circle and this circle are the same, right? Meaning if P is equal to NP. We don't know yet. You might generally say, hey, you've been talking about it for half an hour. Isn't it NP more complicated and difficult? Yeah, in general, that's how it looks. But we haven't theoretically proven that P and NP are equal, right? So more than 30, 40 years, the Clay Math Institute posed, I think, 24 problems. Each one is called the Millennium Problem. And P equals NP question mark is one of those. So if you can solve that, meaning if you can show clearly that either P is equal to NP or P is not equal to NP, there is $1 million waiting for us, right? So it's been a tough thing that we are not able to really figure out. So at this point comes quantum computing. So we are talking about all these P, NP, and what's solvable in how long. Then we keep hearing about quantum computing that's coming in, and then it can solve everything in no time. So all these hierarchies, it's all going to fall apart, and we don't need to worry about any of this, or what's going to happen to all our security things, right? So let's just get into quantum computing just a little bit. So there are a lot of material on the net. I even read like books that I then realized it's all nonsense. So there's a lot of material, but there is a lot of nonsense material there as well. So need to be careful about what is it that you are reading, learning. So we'll just give you a quick overview of how quantum computing is different from our traditional computing, just in the next few slides. Then we'll go back and see what happens to this problem hierarchy when quantum computing really becomes a practical thing, right? So we'll start with this Q bits. So in traditional computing, you know bits. So there is one bit, it can be either 0 or 1, transistor, current passing, not passing. That's it, right? So you can encode just one bits either as a 0 or 1, and that's about it. The equivalent to that in quantum computing is called qubits. So again here, you can use it to code 0 and 1. But the interesting thing is, until you actually measure, it could be anything in between, right? That's not possible. That's not practical. That's not happening in traditional computing. But in quantum computing, that's possible. So qubits, it's in some sort of probabilistic location value somewhere in between. So think of it as from 0 to 1. it's at some state. If you heard of Schrodinger's cat thing, the thought experiment in physics, it's like that. It's neither 0 nor 1. It's somewhere there, right? But when you open the box and then see whether the cat is alive or not, it can be only in one of two states. It's either dead or alive, if you've heard of that experiment. So similarly, when you actually measure it, when you actually in quantum computing go in and then see what the qubit value is, you will always get one value. It will either be 0 or 1, right? But during the computation, when it is taking place, it can be all over. That's not the case in our traditional computing, right? It can only be either 0 or 1, but here it can be anywhere in between. And not only that, when you have 3 bits here, we only have, each one can be either 0 or 1, and what the first bit is has no effect, impact, anything on the second bit. And what the second bit has no impact on what the third bit is. You can independently set them, right? Whereas here, it's all kind of meshed up. So the qubits are in combined state together. So it's not just 0 or 1 here. Here itself, I said it's in some probabilistic state somewhere in between. It's pointing 0.75 or something. Here it's pointing here. But this 3 things together, they hold a combined value that's affecting each other. So it's not just independently one bit, but it's what this is doing is actually touching the other 2, and they have a combined value, right? But so that whole thing is called superposition, meaning it can be everything at the same time. It can be anywhere between 0 to 0.1 to 3 to 0.9 to 1. It can be anywhere and everywhere. It's called superposition, meaning it can presume all the values at the same time. But when you actually look at it, when you really go and measure it, it either becomes 0 or 1. It collapses and then it becomes just like one value, right? What's the point of all this? Is it's because this can take this avatars or this values that are like fluidly flowing between all over the place. Even when you turn one, if you change this, or if during the computation, if this value changes from this probability to this probability, it's going to affect everything else out there as well, right? It may sound confusing, but that's called entanglement, meaning when one qubit value changes, it's like affecting all the other qubits adjacent to it as well. So using this model, so even if you have 2 qubits, it's not just 0, 1, 2, 3. It's not just 2, but you can put in so many different values that are possible between just these 2 values, because doing something here affects this also, right? So the number of states that you can do, it really becomes a large number. And if you really go into and then start looking at it, what's actually happening is, let's say there are 2 bits. They are all kind of like atomic spins that are happening at the really molecular electron level, right? That's what we are talking about, the electron spin, whether it is left or right. If it's left, it's 0. If it's right, it's 1. So it's kind of not really spinning very clearly, but it's kind of wavering, just existing in some form of energy. That's why it's not clear. It's not 0 or 1 like a digital computer situation. But when you do this computation, it's like throwing a little stone in a pond, right? So it starts creating these waves that's expanding. Then you throw another stone that creates another wave. And when they actually interact, go over each other, you start seeing all these patterns where in some places they are actually like helping each other, and then the wave becomes sort of bigger. In other cases, it becomes smaller or like cancels each other out. That's what is happening in quantum computing, right? Maybe confusing, but what we need to understand is the idea here is, again, going back to that ABCDE thing, you basically do a quantum computing code that is going to solve that problem. The way that you solve is not by starting with 0, 10,000 and then 10,001, 2, 3, etc. You code it in 5 bits that can take any value, and then somehow you coax it so that slowly comes up And when you open it and see what is in there, it will have only that one value that you actually want, that particular value where that ABCDE is equivalent to EDCDA, right? Is it possible? Is it even making sense? Yeah, it's making sense. And that's the most beautiful thing in quantum computing, okay? So let me show you one small video, just a couple of minutes. It's a video that's on YouTube. It's about 40 minutes long. You can go watch it. I'm going to show only like 1 minute of it. Keep thinking about that ABCDE problem, because that's not what they are talking about, but you will see why I'm mentioning that. You will see that later in the video, right? It's between Brian Greene, who's a physics author, professor. He's written a bunch of books that are interesting. And then Seth Lloyd, who's a quantum computing prof in MIT. So these two are talking about quantum computing. This is just a 2-minute video, okay? This is Lloyd.
And so the goal is presumably to make use of this weird kind of probability that's inherent to quantum mechanics, where, as we said before, it's not just positive. You can have these interesting interference effects that, if you were really clever, you'd be able to take the various waves and their various probabilities and somehow combine them so that the combined wave doesn't have all possibilities at random, but rather is getting closer and closer and closer to some unique answer. And if you are clever in building your quantum algorithm, that unique answer that we see being built up from all these quantum waves will be the answer that you're looking for, even though you did not know what the answer was. That sounds incredibly difficult. But, you know, just sort of visually, in the quantum computer, if you had all these possible outcomes of your many qubits, you'd want to somehow choose those waves to interfere and begin to suppress most of the answers that you don't care about, because they're not the answer of interest, and bring to the fore the few or maybe the one answer that you were actually looking for.
Nice graphic.
You like that? Huh?
Yeah, exactly. That was well put. Exactly. Yeah, you've got to make, you have to make all these different possibilities, but they're possibilities that exist simultaneously in a quantum mechanical fashion. You've got to make them add up to give you the answer to your problem, and that's tough to.
Okay, I hope you can kind of relate to what I was talking about, right? So there are 100,000, as I said, in the ABCDE problem, you figured out, hey, A cannot be anything more than 1 or 2, right? So that's, you can code that in quantum computing code, then it's going to like delete all those out, and then you have some left. And then you take E, when you multiply that by 4, you need to get A, because when you flip it, it's going to come out. So again, that reduces the combination of numbers that E can be in, right? So that way you are like reducing the space, and then you are finally picking out 1, right? Why am I talking about this? That this is how quantum computing works. So often in the media, people misrepresent, and then they just say all our existing computers are going to be thrown out, and then we are going to put quantum computers in there. No, that's not going to happen. Our traditional computing is really good for a lot of things, and we'll continue using them. But there are a lot of problems like this optimization, or finding out the perfect protein folding model, this and that traditional computing cannot do well, right? That we can code it in quantum computing, and it can do really, really well.
So
that's what
goal is, and so the
looking for. So what are the major components to remember here? First, we said qubits, right? So it can be the 0, 1 bit equivalent, but it can be all over the place. So it's roughly equivalent to digital bits. Superposition, that's a range of value 1 qubit can take, right? Entanglement, that's because if you modify, change, do anything on 1 qubit, it's going to affect the other qubits also, because they are all kind of tied together, right? Interference, that's the process that makes one state more pronounced when measured. So somehow you need to coax, as they said, like drop out all the incorrect values and then like bring it all together to one value. So when you open the box or you measure it, you get that particular value. That's that process, right? And the measurement, in Schrodinger cat situation, you open the box and see whether the cat is alive or not. That's what you're doing in quantum computing. So when the computing ends, you didn't know this is the answer, but somehow you are guiding it and then the correct answer pops up, right? So if you can do all that, is it really possible? I mean, this all sounds like wizardry, not really possible, but it is. So there is one guy, Peter Shor, he came up with an algorithm in the 90s that can be used in quantum computing that does factorization, right? Of course, we still haven't built big enough quantum computers to run this at full speed, but we are still at like 100 qubits and so forth. We are getting there. It's getting bigger and bigger. So factorization, that's really, really important when it comes to secure transactions on the internet, right? So the Shor algorithm, given a bigger quantum computing, can just do it in polynomial time. You don't need thousands of years to do that. That means all our banking security, et cetera, will all just collapse, right? That's why people are worried, and companies are slowly starting to put in modified algorithms that are quantum computing proof. So even if that comes in, it won't break, right? But I've read articles saying adversarial nation states are gathering everything that's out there and then archiving it in their databases, so that when quantum computing becomes possible, they can go and crack everything and then read whatever was there that was all currently unreadable, right? So need to move. Grover algorithm is another one that's for search. So again, we kept talking about sorting, searching. So there is a quantum computing version of search. There is variational quantum eigensolver, and then there is quantum unconstrained binary optimization. So these are all existing, fully certified, qualified, verifiable quantum algorithms that can be coded, provided we have a big enough quantum computer that can run and solve these, right? So you are saying now we can do non-deterministic polynomial time computing using quantum computing in polynomial time. Does that mean all the thing just collapses? Not really, right? So that's what this particular hierarchy is showing. So this is like the P that is still there. Previously, we had this BPP, that's bounded error probabilistic polynomial time. Now it's become quantum polynomial time. So what is quantum computing can do in polynomial time? Bounded error, because we are just trying to reduce the error as much as possible, right? So if you can really make the error zero, then you are always getting the perfect answer. Maybe possible, may not be possible, but if it's not possible because the combination is too much, quantum can do a better job. So you can bound the error as much as possible. It may take a little bit more space or time to do it, but you can still do it. So you can still see NP complete is not collapsing into this, right? So this hierarchy still exists. So this is the whole point of, I mean, go read up about quantum computing, but you will still realize that this hierarchy doesn't collapse. It's still there. There are problems that are not going to be solved even when quantum computing comes in. So we said we don't know whether P is equal to NP. Then there are these really neat code. So if P is equal to NP, this Scott Aronson basically said this means it's creative leaps, meaning anyone who can appreciate a symphony can also create it, right? So if you can appreciate a symphony, you could be Mozart, kind of. Anyone who can recognize a good investment would be a Warren Buffett kind of thing. But what about the other way? If a P is not equal to NP, that means the world of mystery, difficulty, frustration, that's kind of the world that we are living in. So if we need to make a bet, we'll probably say P is not equal to NP, but we still don't know, meaning it's not been very clearly proven, right? So having said all that, are there really, how many problems that are there? There are tons and tons and tons of problems that are NP hard and NP complete. It's been clearly proven. These are all sample ones. You can look up any one of these, I mean, just graph coloring or Hamilton cycle, traveling salesman, you can see here, right? So these are all problems that are there. But the idea here is, if you can take any new problem, I mean, this is not something just like God given, right? So in my graduate school work, I actually took this problem of bandwidth allocation. So let's say you have a fiber and you have a bunch of traffic that's coming in, and you need to accommodate all that and then make good use of the fiber that's there, right? So I called it bandwidth allocation problem. That can be proven. I could prove that it is an NP complete problem. So if you can solve traveling salesman problem in whatever amount of time space, then my bandwidth allocation problem can also be solved using the same algorithm. That's the idea here, right? And if you really go up and look at it, this is called satisfiability. There's 3 satisfiability, graphic 3 color, blah, blah, blah. There are all these problems that are already set up, classified, analyzed, and then listed as they belong to this category. And if you can come up with a good solution for any one of these, then you can use the same solution to solve any one of the other problems also, right? This SKCD thing you can just read. So as I said, it's not just for just theoretical analysis, like traveling salesman problem being exactly applicable to Amazon delivery truck person. These things have real world application immediately, right? So you do need to think about, understand, and when you are coding, need to make sure you are doing the best you can to like reduce the amount of time and space you are going to take. That's where optimization comes in, right? But if you are stuck, if you are there and you realize that it is an NP-complete problem, what can you do? You cannot write a perfect solution that will give you the exact most optimal answer everywhere, right? So you need to go to one of these heuristics method. So it could be a neural network that does some analysis and then gives you some solution, machine learning, AI. It could be simulated annealing. We'll talk about what that is in a second. Ant colony approach, or genetic algorithm. These are all heuristics algorithm, right? Meaning it will do a computation, it will give you a solution, not guaranteed that that's the most optimal one. This is what is currently going on when UPS truck driver has to touch 100 homes. It will come up with some solution that's more optimal than randomly going from A to B to C, but most probably it's not the most optimal one, right? And you really want to spend all the time to create the most optimal one, the whole day is gone, and so you it's useless. That it need to be, packets need to be delivered that day, right? So what are heuristic solution and what is simulated annealing? Just touch upon that and then wrap up. So annealing is, as you may know, the term means like heating, for example, iron, right? When it is solid iron, you can't like bend it, it doesn't ply. So you heat it up. So when it's really red hot, you can beat it up, make it extend, make a sheet, make it bend, do whatever you want, right? So it's more pliable when it's at a high temperature. We mimic that idea, and of course, when it cools down, comes to the room temperature again, it becomes as solid as regular steel, right? So it doesn't lose that physical characteristic. We bring that idea into solving something like a traveling salesman problem, right? So you take the problem, again, traveling salesman is easy to visualize, so I'm just saying that. So just take some random connection list of the cities that you can think of, right? So you have, let's say 26 cities, A, B, C, D, just start A, B, C, D, E up to Z, right? And then simply compute how much time, or let's say you are trying to optimize for distance, compute the distance from A to Z and then coming back to A. Maybe it comes out to be 100,000 miles, right? Then just go and change one link, maybe from P to Q, change it to P to R and then R to Q, right? So just flip one somewhere and then again compute and see what is it. Has it actually reduced just a little bit? If it is, maybe you want to keep it. Maybe you are moving towards a more optimal solution, right? If it has actually increased the distance, maybe you are going in the wrong direction. So you don't want that. So maybe you will put it back the way it was. So you keep doing this over and over and over and over and over and over again, right? As you do that, if you consistently keep picking up changes that keep reducing the total distance, maybe you are going towards a more optimal thing, right? So if you always move that way, like every switch, if it's less, you keep it. If it's more, you toss it and then go back to the previous situation. That's a very greedy algorithm. That's a heuristic. You can do that, run it for so much time, and beyond that, you realize anything that you change, it keeps increasing. So you give up saying, hey, this is all I could do, right? So that's a greedy approach. But in simulated annealing, initially, it's like the metal is really hot, right? At that time, you put a probability on, and the probability is close to 1. So at that point, whether it goes up or goes down, it's okay. You just accept, right? Whatever changes that you can think of. And then maybe the distance actually from 100,000, it became 102,000. But initially, you will still accept. But you keep doing this cycle over and over and over. And then slowly you keep turning the probability down, right? So initially it's close to 1. Eventually, after, I don't know, 10,000 cycles, 10,000 swap, every time you keep turning that knob down, then you are close to 0. That means at that point, you are no longer going to accept any flip that is actually giving you a longer distance. That is equivalent to the iron actually getting cold. So you are really heated it up. So you can beat it whichever way you want. And then as it keeps coming down, you are cooling the metal down. So that's kind of what is called simulated annealing. And you define some time for which you are going to run this. And then by the time it comes to 0, if you no longer see any improvement, you say, okay, this is the best I could do right now, right? So that's simulated annealing. What is the problem there? It's because, let's say you start from here, right? And then you go up, you come down, and then eventually maybe you will get stuck in a local minima, and you already come down, the probability has come down further. And then if you try to go here, it's going to reject, because you will accept increase in distance only in the beginning. Hope I'm making sense, right? So you will get stuck in this local minima, and you will never get to this global minima, right? So that's the problem with this heuristic approach. You will get some solution, not guaranteed that it's going to be the global minima. So it could go from 1 to 2 to 3 to 4 to 5. Maybe here you are maximizing. Hopefully you will get to this 9, but you may get stuck, and then you may end up with a 5 as well, right? So that's a problem in general with the heuristic solution. Plus, since you are not hitting the actual final exact optimal solution, each time you run it, you will get a slightly different solution as well, right? So that's what you end up with. Another heuristic approach is this ant colony optimization. You might know this. So this is source, this is destination where there is food, right? Ants, when they initially start, they'll go all over, right? And eventually when they find food, they'll come back. And when they come back, they keep leaving these pheromone hormones. And other ants can sense that and then keep following that more and more. And so initially, this is the path they used to bring food back. But then somebody went this way, and then somebody, and pretty quickly they'll come to this straight line path, right? So this is how ants actually behave. And we try to mimic that in our approach. So you again take your NP-complete problem for which you cannot find a perfectly optimal solution. You throw in a bunch of ants equivalent to changing this and that, and then trying to see how things work. And you can mimic the ant colony approach to, again, get to a reasonably good solution, right? So what's the actual takeaway? So what's going to happen? So any problem that you have, you basically need to assess the problem difficulty, right? So if you start with adding multiplication, easy peasy, you know what's happening, and so no big problem. But if you keep going into sorting and tiling and traveling salesman and so forth, slowly it becomes much more complex. And so anytime you try to code something that will exhaustively look at every possible solution to find you the best possible optimal solution, most of the real world cases you are going to fail. We are talking about even a 100-point UPS driver thing is, it take days to figure out, right? So assess problem difficulty and always code your solutions in the most optimal way, because when you do a smaller one, small problem sizes, the amount of time it takes may look trivial, but as soon as you hit the problem size, the N becomes bigger and bigger. The time it takes for your code to run may really shoot up. So you always want to be cognizant of how optimized, how cool, how good your algorithms are. If the problem turns out to be NP complete, meaning it belongs to this class that you can reduce it to other problems and show that it cannot be solved in a reasonable way, then you basically throw your hand and you are ending up only with heuristics. So you need to figure out what heuristics model is reasonable for you to apply. Then you can turn the knobs, right? So like I said, in case of simulated annealing, maybe for the UPS truck driver, you can run the code only for 10 minutes in the morning. You need to give a solution to every one of the driver, right, before they depart. So you can run only 10 minutes. So you are going to turn the knob pretty quickly from top to bottom. Maybe you have some ideas about, hey, at rush hour, if you go to that part of the town, it's always stuck. So you maybe put that in the other end, that kind of optimization you can throw in and try to do that faster, right? But if you take even 2-3 hours to come up with a reasonably good thing, half the day is gone. The drivers want to leave at 7 a.m., right? So you need to figure out what's the heuristics that you can apply to solve the given problem on hand. Is bringing quantum computing going to solve it? No. So you still need to be aware of this, right? So I just wanted to play this one video. This is my last slide that shows the same traveling salesman problem in an animated way. You can just see how it works in simulated annealing kind of model, where you take two cities, flip it, and then see how much it reduces, right? For 3 or 4 cities, the possible routes are 10 power 264, right? That's my last slide. So thank you. And I hope you can tell.
Opportunity open for questions. So any questions, please feel free to ask.
Sure.
With the recent announcement of the Nobel Prize winners in physics, where they predicted that quantum effects with quantum tunneling can be now observed at a macro scale, compared to like we've seen, for instance, SSDs for 30 years. How do you think this is going to help quantum computing evolve and progress going forward?
When you get into quantum computing, there are so many aspects. I mean, of course, many things that we talked about, each one can become a semester-long course here, right? So just the mini macro if you just take quantum computing, to really be able to observe everything, any little thing, when you breathe the quantum level, something changes, right? So you need to super cool everything. And that's the model Intel and IBM, we are all trying, right? The super cool state basically avoids unnecessary interference and then reduces. So things like, oh, you don't need to do it at the micro level and you can do it a little at a macro level. It maybe will eliminate some of these needs to like take it down to such temperatures, right? Which immediately translates to money, because you no longer need to, I mean, basically producing a computer is not that difficult. You don't need to keep it in a basement at like super cool temperature and so forth, right? So it has like real implication. And what is it that you are going to even use to measure, I mean, to store the state of 0 and 1? That's not decided. So I can give you references, you can go see. So there are things like spin is what I talked about. There is temperature, there is color, there is like any like subatomic particle level characteristic that you can pick can be used to like basically store the state, right? And it should like move about and do things. So if you really don't need to go to lowermost level where operating things are really, really difficult and it's extremely sensitive, and you can up level one bit, it's like a big relief, and it can really be useful in designing computers that are cheaper, easier to use, more easier to approach.
Thank you. Questions? Comments?
So with quantum computing, I mean, right now we're solving problems like the traveling salesman problem. Heuristically, we're approaching
Yes.
the optimal solution. Would it be more appropriate with quantum computing to be able to brute force something like that? If we can, say, well, it's only 10 to the 624, and we can solve that with quantum computing. This is a brute force instead of a heuristic approach then.
Yeah, I mean, anything, once you define the problem size to an actual number, then I mean, most of these things becomes easier, right? So take adding two numbers. I'm talking about how long it's going to take in terms of n, because I want to define it for any possible size of the number. So if it's 1 million, 1 trillion, infinity, doesn't matter. I'm saying it's going to take n units of time. If you're saying my maximum number is going to be only 100 digits, then yeah, I mean, I can tell you it's not going to take more than 100 units of time. Maybe I can come up with a faster processor that will even do it in traditional computing. And if you're saying it's 1 million, maybe quantum computing can do it a little faster. Everything is possible. So as soon as you put some limit and then say, my problem is not going to be anything bigger than this, a lot more solutions become possible, right? In fact, that's how we got into this Y2K kind of thing, meaning we said, our code is not going to be there for 30, 40 years. So 2 digits is enough for year. And then we got into that trouble. So something along those lines. I'm sure you all heard about in year 38, the Linux thing is going to like run out the time thing, right? So we are not talking about any like limited size computing for which we can certainly develop, and we do need to develop solution. But these are mainly thinking about irrespective of the size of the problem. If the size is n, what can you do? Is it n square, n cube, or is it 2 power n, 10 power n? And so it's like becomes impossible, right? If the n goes to the superscript, we are done. So we need to come up with some heuristics. If the n stays as the main number and then you are using a constant in the superscript, then we are good. It's polynomial.
So because of an exponential problem, polynomial problem.
Yeah.
Okay.
Yeah. But as long as, even if it's an exponential problem, like we said, if the UPS salesman has to go only to 5 places, well, I mean, we can figure it out, right? So it's not going to take that long. So as the problem size becomes smaller, even if it's going to explode later, it's okay, as long as you always say it's never going to be more than n, where n is really small, then we can come up with some other solution, right? So the idea is to repeatedly think, irrespective of putting a physical number to it. If it's just some n, where do we stand? What can we do? And is it possible to work with it? Right? That's the main question.
So
Robin salesman blow up faster than factorial?
Yeah, it's exponential, right? So yeah, more than, yeah, it's exponential.
Factorial, it blows up pretty fast.
Sure, yeah.
Not solving
This is even, yeah, this is even.
It's related to factorial complexity.
You saw that last TSP analysis for like 324, there's like 10 power 324 something. I mean, 10 power 324 is like it's much more than factorial. It becomes like exponential thing, right? So if the n goes to the superscript, you're dead.
Okay, another question. How do we protect anything if, well, it's been a lock and key approach before. Now we can, put a bound on it saying, well, if I try these, couple billion combinations, I can, break into a bank account. How do we protect it?
Yeah.
From this quantum computing.
That's a big thing. And now people are coming up with the quantum proof thing, not by just expanding the number of bits, because previously, if you have only like a 286 computer, maybe even if you have like 10 bits, it's going to take a long time or something, right? So maybe now you have 64-bit computers, maybe your RSA keys are 256 or 512 or 1000 bits long. So far it's been just expanding to more number of bits and believing that that will save us, because even the fastest supercomputer will take so long. Now the algorithms are totally changing. So you can go dig into quantum proof factorization, not factorization, the security algorithms. It's like that Shor, was it Shor or no Shor? Let me see what was. Yeah, no. It's. Yeah, yeah, it is Shor. Yeah. So if you really dig into Shor algorithm, that's quantum proof. That's basically what will be used. I mean, Apple and others have started deploying. I mean, Shor algorithm is actually do the factorization in quantum computing. So Apple and others have started deploying newer versions of this security key algorithms that Shor algorithm cannot resolve, cannot break. Right. So even if you get to quantum computing, the newer versions cannot be broken because it's not based on simple factorization.
Well, thank
Thank
you very
you.
much. We do have something here. Is welcome to your bug clubs.
Yes.
You guys switch to something else. They're like a phone charger or something.
In Saturday Night Live, right? So the people who do like 5 times hosting, 7 times hosting,
Yes.
like a jacket.
Get something else special, like upgrade, right? You've been here long enough at AITP. I think every year we invite you back, on a different topic.
Thank you. Yeah.
Thank you very much for this information. So,